right, so let's put everything together with this example. We've got CH2O, and they're going to ask me to draw the Lewis structure and all this other fun stuff, and we might even add in a few things. And we'll make this like anything you could ever want to know about the CH2O molecule. Anything they could ever ask me, like on an AP free response question, or I guess multiple choice for that matter. Let's start by drawing the Lewis structure. That's usually part A. So the carbon's going in the center because I know he makes the most bonds. There's a carbon. 1, 2, 3, 4. I got 2 hydrogens. I can put them wherever I want, and I know they will only single bond. They only have 1 valence electron. And then I've got the oxygen. Ooh, this is perfect. Oxygen always has 6 valence electrons, 2 single and 2 pairs. So I'm going to kind of rig it and line up the single electrons so that I can link them up in a double bond. So again, don't try to memorize, is this a single, double, triple? Just kind of figure that out as you start sketching the structure. Awesome. So I'm going to have a double bonded oxygen and then single bonded hydrogens. Carbon is all good. A couple other things that they might ask me for. Things that aren't in this picture, but they are in this example, but they might ask me for. They might ask about like bond polarities. Let's see, they ask about bond polarities. Bond polarities. So they might say something like, hey, the carbon-hydrogen bond, is that a polar bond or a non-polar bond? And for that, I can kind of look at the periodic table and think about electronegativity. I know that fluorine has the all-time highest electronegativity on the periodic table. And as I get closer to fluorine, electronegativity increases. I also know that there's something called nuclear charge. As the nucleus becomes more positive, as there's more and more protons, there's a stronger pull on the electrons, the existing electrons in that particular atom, as well as electrons from neighboring atoms. So in this bond, the electrons should be held closer to the carbon. Carbon's going to have a little bit higher electronegativity, so I would have a little slightly negative carbon and a slightly positive hydrogen. If they ever ask about bond polarity, that's what they're referring to. In this one particular bond, the carbon-hydrogen bond, is it polar, is it non-polar? And then they might ask you to indicate the polarity. And that's kind of what we did with those partial positive and partial negative symbols. So we would say this is a polar covalent bond. I know it's covalent because it's non-metals. We could do the same thing with the carbon-oxygen bond, the carbon-oxygen double. But this time, oxygen has the higher electronegativity. It's closer to fluorine. It's got a greater nuclear charge, more protons, so there's even going to be a stronger pull on electrons. So it's still polar, but this time the partial negative goes to the oxygen, and the carbon would be partially positive. Cool. So there's bond polarities, and it's not asked for in this particular question, but it's definitely something that they could ask you about. They might ask me for the Vesper shape, and for that I'd look at my Lewis structure, and I may not have drawn this to the true three-dimensional shape, but around my carbon I can tell that there are 3 regions of electrons. 1, 2, 3. 3 regions of electrons will repel and orient themselves as far apart as possible. So in real life, I'm dealing with the trigonal planar geometry. So this might really look like in a ball and stick structure, something like this. Or again, I don't have to draw my Lewis structure to the true bond angles, but really it might be kind of like that. And then I should probably put those extra pairs on the oxygen to show he has an octet. Again, you don't have to draw it with 120 degree bond angles. My original Lewis dot structure would be 100% acceptable. But if they ask me for the shape or the geometry, I would say it's trigonal planar. If they ask me for the bond angles, I would say, well, in real life, those bond angles are 120 degrees. Your dot structure does not need to reflect that. Okay, so those are some good things. We got the Vesper shape. We got the bond angles. That's good. Other things that they might ask me for. Determine the hybrid orbitals needed to describe the bonding in this molecule. Okay, now when we talk about hybrid orbitals, we're not going to include hydrogen. So let's kind of do a little hybrid orbital. La la la. Hybrid orbitals. Hydrogen? None. He only has that one s orbital. So if you only have one orbital, you can't hybridize. You need at least two orbitals to hybridize. So hydrogen does not have hybrid orbitals. Obviously carbon does, and we kind of talked about carbon in the last couple videos. Around that carbon, we need 3 bonding regions. 3 bonding regions, we need 3 hybrid orbitals. So we're going to hybridize the s and 2 of the p's. That gives me 3 hybrid orbitals. sp2. And again, anything based on the trigonal planar shape will be sp2 hybridized. So that could be the true trigonal planar, or it could be the bent that had the one set of extra lone pairs and then 2 bonds. Anything based on a trigonal planar with 3 bonding regions. sp2 hybrid. Now this might not seem obvious, but what about oxygen? Look at the oxygen. Around oxygen, there are 3 regions of electrons. There's the double bond, that's a region of electrons. And then there's the 2 lone pairs. Wow. 1, 2, 3. There are 3 regions of electrons around that oxygen. Now, they don't have to be bonding regions. They could be regions of lone pairs. But we need some place to put those lone pairs, and they do repel. So when I think about oxygen, I need 3 orbitals to put electrons, sp2. Again, they don't all have to be bonding regions. I mean, one of them is a bonding region. But the other hybrid orbitals on oxygen are going to get the lone pairs. So picture this in your head. On oxygen. Okay, here's the oxygen. Da-da-da. Oxygen. Here's his, I'll try to draw the hybrids. 1, 2, 3. Oh, that's not bad. So let's say these are the 120 degree apart sp2 hybrids. sp2, sp2. And that's oxygen in the center. I better mark that in. Oxygen. O-X-Y. Oxygen. Okay, so 2 of those sp2 orbitals, those hybrids, 2 of them are going to get the lone pairs. These lone pairs need to go someplace. Bingo. We could put them in the hybrid orbitals. And they may ask you, hey, what is the angle between those lone pairs? 120 degrees. Because again, there are 3 regions that will all kind of repel. I want to get as far apart as possible. So around the oxygen, count the lone pairs. Some people will look at them and be like, oh, there is no hybrid or whatever. No, there really are 3 regions of electrons on the oxygen. Count the lone pairs. And be really careful with things like oxygen and nitrogen that typically do have lone pairs. Let's say you're doing like a multiple choice question on the AP test, and they give you a structure sometimes, this is totally mean, they don't put the lone pairs in their Lewis structure. You got to write those in. Be very careful with especially things like oxygen and nitrogen. If they don't have the lone pairs drawn in their picture, it doesn't mean that they're not there. So I always look for that on oxygen and nitrogen. Put them in, because that's going to help explain the hybrid orbitals and the angles around the oxygen. Now this extra guy in here, this is going to bond to carbon. This extra guy right here, that's going to overlap with one of the sp2 hybrid orbitals on carbon. Oh, cool. Okay, so now don't forget that with the carbon and the oxygen, we've hybridized 3 of the orbitals, but we still will have an unhybridized p. They'll both have an unhybridized p. That's what's going to overlap to form the other half of the double bond. So, I mean, this really is going to look similar to the C2H4 structure. But now picture this as, instead of a carbon, picture this as oxygen. And then instead of these being single bonds to hydrogen, these will be the lone pairs. Otherwise, this is really similar in structure. If I pretend that this is an oxygen, then the hybrid orbitals here would contain the lone pair, and I wouldn't have these extra pink or red ones, the hydrogens. This would contain the lone pair, and then the extra unhybridized P on the oxygen would overlap with the extra unhybridized P of the carbon. Can you kind of see how this is really similar? But what I like, and it's a good example of the fact that lone pairs need to go in an orbital. So again, just because it doesn't look like there's any other bonds around oxygen, doesn't mean that we don't need orbitals to put those lone pairs. So you got to think of the lone pairs as needing an orbital. So around oxygen, I need 3 orbitals to put electrons. 3 equal orbitals, sp2, 120 degrees. So that kind of brings me to the other question that they might ask us. They might say, how many sigma, how many pi bonds are in this structure? And we would say, piece of cake. Single bonds are always sigma. So I know there's 2 sigma bonds from the overlap of the hydrogen 1s orbital and then the carbon sp2 hybrids. Those single bonds between carbon and hydrogen are sigma. A double bond is always a sigma and a pi. So in total, there should be 3 sigma bonds and 1 pi bond. 2 of the sigmas are the single bonds with hydrogen, and then the double bond is a sigma and a pi. Holy buckets. Determine the hybrid orbitals, need to describe the bonding in this molecule. I think that's everything they could possibly ask you about the bonding in the CH2O molecule. And really, that is like a great example of anything in general they could ask me that involves bonding. So if you can tackle something like this, you are golden